let me find the page. Okay, you remember that yesterday we deduced heuristically the so-called drift diffusion equation. That is an equation that provides the expression for the current density of electrons or holes in the semiconductor. In doing so, we also define some parameters. We define the diffusion coefficients and the mobilities, and then the conductivities, okay? So it is convenient now to shortly go through these parameters in order to have an idea about the order of magnitude of each parameter. This is done in the next page. First of all, the mobilities and the diffusion coefficients in the frame of the drift diffusion model are not independent from each other. Actually, it can be demonstrated that when you consider the electrons, the diffusion coefficient of the electrons is equal to the mobility of the electrons, mu n, multiplied by kT over Q. And similarly, the diffusion coefficient for holes is equal to the hole mobility times kT over Q. These two relations are called Einstein's relationships, and they are much more general. They also apply to other types of particles, not necessarily only to electrons and holes. So now we can determine the order of magnitude of these quantities. Assume that we are at room temperature, so we take TL equal to 300 Kelvin. By the way, the temperature is called T sub L because L stands for lattice. It's the temperature of the crystal lattice, okay? So if you take TL equal to 300 Kelvin, then you have kT over Q is calculated. You remember the Boltzmann constant is 1.38 times 10 to the minus 23rd joule over Kelvin. And the modulus of the electron charge is 1.6 times 10 to the minus 19th Coulomb. So globally, this gives about 26 millivolts. So kT over Q has the units of volts. Its value at room temperature is about 26 millivolts. And kT over Q also takes a name. It is called the thermal voltage. The inverse of the thermal voltage, that is Q over kT, is also important, because, as we shall see, it appears in the exponent of some expression that determines the current of the p-n junction. So at room temperature, Q over kT is about 38 volts to the minus 1. Then we can make an estimate of the value of mobility. The mobility of electrons and that of holes are different, but they have the same order of magnitude. So this estimate works for both, okay? So you remember in the definition that we gave yesterday, mobility is equal to the electron charge times the statistical average of the momentum relaxation time divided by the effective mass. So Q as above. A reasonable value for the average relaxation time for momentum is something less than a picosecond. So we take 0.25 picoseconds. And the effective mass is smaller than the free electron mass. So we take 0.4 10 to the minus 30 kilograms. Okay, the electron mass is about 0.9 times 10 to the minus 30th kilograms. Okay, so globally, if you put these numbers together, you find about 1,000 for the mobility in the standard units that are used in semiconductors, that is square centimeters divided by volts divided by second. Then we can make the estimate of the diffusion coefficient simply by taking the Einstein relation. So mu is about 1,000, kT over Q is about 26 milli. Let's take 25, okay? So we have about D equal to 25 centimeters square over second, okay? At room temperature. Then we can make an estimate of conductivity. For instance, we take the conductivity of the electrons. You remember, the conductivity of the electrons is equal to Q times the mobility times the concentration of the electrons, okay? And we can perform this type of estimate considering different cases. We can consider, for instance, a conductor. You remember, in a conductor, the mobility is similar to that of a semiconductor. But in a conductor, the concentration of the electrons in the conduction band is much, much higher than in a semiconductor, okay? Then we can consider an intrinsic semiconductor like silicon. Then we consider a doped semiconductor with some dopant concentration. And finally, we can consider an insulator, okay? From our analysis, you remember the insulator has no electrons in the conduction band and no holes in the valence band. Actually, there are few electrons, not so many, in the conduction band of an insulator and few holes in the valence band, but not enough to provide a significant conductivity, okay? So globally, we can assume that mobility is 1,000 in all cases, just for the estimate, okay? And the electron charge is something times 10 to the minus 19th, okay? So the product gives you something like 10 to the minus 16th square centimeters over ohm, okay? And this must be multiplied by the concentration of the electrons, okay? So if you take the 4 lines that you see here near the brace, then assume that in the first line we are considering an insulator. An insulator may have 10 to the 4th electrons per cubic centimeter in the conduction band, which is very small, okay? So if you have 10 to the 4th times 10 to the minus 16th, you have 10 to the minus 12th ohm centimeter to the minus 1. okay, for the conductivity. So the conductivity of an insulator is non-zero, but really very small, 10 to the minus 12 in these units. The second line refers to silicon at room temperature. You remember the intrinsic silicon at room temperature. The intrinsic concentration of electrons is 10 to the 10th, more or less, okay? So you have 10 to the 10th times 10 to the minus 16th. You have a conductivity that is 10 to the minus 6th, which is still very small. But as you can notice, it is 6 orders of magnitude larger than that of the insulator. On the third line, we consider a case of silicon doped with donor atoms having a concentration of 10 to the 17th, okay? So in this case, the concentration of the electrons is 7 orders of magnitude larger than that of the intrinsic case. And of course, the conductivity is 10. So the conductivity is 10 instead of 10 to the minus 6. So you, from the intrinsic case to the doped case, you increase conductivity by many orders of magnitude, okay? But then if you take a conductor, you may have that the concentration of the electrons in the conductor case could be about 10 to the 22nd, okay? So you obtain a conductivity that is 10 to the 6th, which is still many orders of magnitude larger than that of a doped semiconductor like the example of silicon, okay? So you see that the conductivity may range over many, many orders of magnitude, starting from the insulator to the intrinsic semiconductor to the doped semiconductor and finally to the conductor, okay? To continue this discussion about the model that describes transport in semiconductors, it is convenient to distinguish some symbols, okay? You remember at some point yesterday, we split the global continuity equation into two continuity equations. One is for the electrons in the conduction band, the one of the left on the last line, and the other one is for the holes of the valence band. And we also gave a meaning to symbols Wn and Wp, okay? Wn is the net generation rate, that is the difference between the number of electrons entering and those leaving the conduction band per unit volume and time. So Wn and similarly Wp embed all the possible types of transitions that change the population either of the conduction band or the valence band, okay? In many cases, it is convenient to distinguish what are the reasons for these transitions, okay? So in all cases, if you have a transition of an electron or of a hole from the conduction band to the valence band or vice versa, or even from a trap belonging to the gap into a band, okay, or vice versa, okay? All these transitions anyhow imply an exchange of energy with something else, okay? An electron or a hole that makes a transition exchanges energy. for several reasons, it is convenient to distinguish the transitions depending on which entity is exchanging the energy with the electron or hole. Okay, so we classify the transitions depending on the other entity that exchanges energy with the electron. A typical example is an exchange of energy of the electron or hole with the nuclei of the semiconductor. Okay, the nuclei vibrate. Okay, so they have an energy. If an electron has a collision with the nucleus, there is an exchange of energy that may go in one direction or in the other direction. The electron may acquire energy and subtract the energy from the nucleus, or vice versa. This is such an important interaction that it is given a special symbol. Okay, so we split Wn and Wp into parts, and one part describes the transitions involving collisions with the nuclei of the crystal. Since the vibrational energy of the nuclei depends on the lattice temperature, these type of transitions are also called thermal transitions. Okay. Then there are other types of transition. For instance, an electron may exchange energy with another electron, or it may change energy with an impurity, or it may exchange energy with a photon that impinges on the semiconductor, and so on. Okay, so all the other types of interactions in which there is no exchange of energy with the nucleus, but there is an exchange of energy with something else, they are called non-thermal interactions. Okay, so after this introduction, we can see how we change the symbols for this. Okay, so we set, you can see it in the last line of the page, W is equal to Gn minus Un. Gn is a symbol that indicates the non-thermal transitions. So Gn is called non-thermal generation rate for the conduction band or for the electrons. And similarly, Gp is the non-thermal generation rate for the valence band. What does it mean? It means that Gn is the total number of electrons that enter the conduction band per unit volume and time, less the total number of electrons that exit the conduction band per unit volume and time for reasons that are not collisions with the lattice, so for non-thermal reasons. Instead, it is customary to reserve a special symbol to the thermal transitions, and this symbol is Un for the electrons and Up for the holes. But it is also customary to describe these as recombinations less generations. So this is the reason for the minus sign. So to be more precise, Un is the total number of electrons that exit per unit volume and time the conduction band due to thermal collisions, that is, collisions with the nuclei, less the total number of electrons that enter per unit time and volume the conduction band, again due to thermal collisions. Similarly for UP, UP is the total number of holes that exit from the valence band less those that enter the valence band for thermal reasons and per unit volume and time, okay? At this point, we can put all these equations together, okay? You remember we have the Poisson equation that is necessary to calculate the electric potential. And the Poisson equation is what is left of the Maxwell equations because we found that it is acceptable in a semiconductor to use the so-called quasi-static approximation. So in the first line, you can see the Poisson equation simply split into two blocks. The one on the left is divergence of D equal to rho, that is one of the Maxwell equations, as you remember, in which the charge density rho is Q times P minus small n plus capital N. And on the right, we see the relation for the electric displacement, that is D equal to minus the permittivity of the semiconductor times the gradient of the electric potential. Then we have the continuity equations and the drift diffusion transport equation. So on the second line, you can see the pair of equations, the continuity equation and the drift diffusion equation for electrons. And in the continuity equation, the original term Wn, you remember, is split as Gn minus Un, and then Un is shifted to the left. So the continuity equation is dN over dt plus Un minus 1 over Q divergence of Jn equal to Gn. The corresponding drift diffusion transport equation is Jn is equal to the drift term. Remember, the drift term is the conductivity of the electrons times the electric field, and the conductivity of the electrons is Q mu n times n, plus the diffusion term Q dn gradient of n, okay? Similarly, we have two more equations for the conduction band. dP over dt, etc., with the expression of the current density of the holes, Jp, okay? This set of 6 equations apply to the semiconductor region, okay? It may happen that a device also has portions of the volume that are made of an insulator, okay? So the model in the insulator simplifies because we may have a fixed charge in the insulator. Sometimes it is built up on purpose. For instance, some types of memories, okay, we inject a charge into the gate insulator of the MOS transistors, okay? Anyhow, the Poisson equation for the insulator simplifies because we do not have electrons or holes in the insulators. We simply have possibly a fixed charge. And obviously we have to change the permittivity because in the insulator the permittivity is different than in the semiconductor. We call it epsilon aux because in typical implementations the insulator is made of silicon dioxide in the standard technology. And the rest of the equations becomes identities, okay? We don't have mobile charges in the insulator, and we do not have current densities, okay? So in practice, in the insulator, we must solve only the Poisson equation. Let's consider the case of the semiconductor, okay? In the semiconductor, you see, we have a system of 6 differential equations, okay? They are partial differential equations because we have the partial derivatives with respect to space due to the divergence operators and to the gradient operators. And we also have the partial derivatives with respect to time of the electron and hole concentrations, okay? What are the unknowns? The unknowns of the equations are the electric potential phi, the electron concentration n, the hole concentration n, and these are scalar unknowns. Then we have the electric field E, the current density Jn for the electrons, and the current density Jp for the holes. Then we have coefficients, and the coefficients are some constants like permittivities, the electron charge, okay? Mobilities to first order can be considered as constants, okay? And diffusion coefficients. So these are coefficients. The data are the dopant profile. And remember, N, capital N is the effective or the net dopant concentration, okay? And possibly the charge in the oxide. Okay, these are data of the equations. And then we have the thermal, the net thermal recombination rates, UN, UP, and the non-thermal generation rates, GN, GP, okay? These quantities are not constants. They depend on the unknowns. So they depend on NP, phi, and possibly Jn and Jp, okay? So the important aspect is that we are able to express these functions UN, UP, and Gn, Gp without introducing new unknowns, okay? So we have 6 equations with 6 unknowns that are phi, NP, electric field, Jn, and Jp. Of course, the displacement vector D is not an extra unknown because it is proportional to the electric field, okay? These equations are non-linear because if you look at the drift diffusion equation, you see that in the equation for the electrons, we have the product N times E. So concentration of the electrons times the electric field. So there is the product of 2 unknowns. So this is sufficient for the equations to be non-linear. And of course, there is also P times E in the equation for the holes. And the other non-linearities are hidden in the expressions of UN, UP, and GN, GP. Okay, so these equations are non-linear. They also have another inconvenience that some of the unknowns are scalars, and that is acceptable, but some other unknowns are vectors, like E, Jn, or Jp, okay? But this can be fixed, because if you just look at the structure of this system, consider the first line. If you bring the expression of D from the second equation on the first line under the divergence on the left, okay, you obtain a single equation with the Laplacian of phi equal to the charge density, okay? So the two equations of the first line, that are two equations of the first order with respect to space, can be combined together in order to provide a single equation whose unknown is the electric potential, and there are also P and N at the right-hand side. So all unknowns of the new equation are scalar functions, okay? So we eliminate the vectors, okay? And we obtain from two equations of the first order, we obtain one partial differential equation of the second order, that is the Poisson equation, okay? We can do the same operation in the second line. We take Jn from the equation on the right and replace it into the divergence of Jn, okay? So you see immediately that, again, we obtain an equation in which the only unknowns are n and phi. But the equation, again, is of the second order, and the same for the third equation. So we can reduce the system of 6 first-order equations into another system made of 3 second-order equations, in which we have to deal only with the scalar unknowns phi, n, and p. And this is what is usually done for the numerical solution of the equation. So this page is very important because these equations constitute the so-called semiconductor equations, or the mathematical model for semiconductor devices. And we shall use this mathematical model from now on to describe the functioning of the semiconductor devices. Of course, we have to say something about the generation recombination terms, UN, UP, and GN, GP, and the other coefficients, essentially the mobilities. Before we continue, we spend a few more minutes on the transport equations, because you can observe that the transport equation, those that provide the current densities, are of the so-called binomial form. So they have two terms. They are made of the sum of two terms, the drift and diffusion term, okay? It is possible to introduce a manipulation that essentially amounts to changing the unknown function, okay, to transform the transport equations into a form that is called monomial. So instead of being made of the sum of two terms, they have only one term each, okay? And we can do this by introducing auxiliary unknown functions that are called the quasi-Fermi potentials, okay? These two unknown functions are indicated with the symbols phi n and phi p. And of course, they depend on space and time. And we impose that the electron concentration can be written as Ni exponential of Q over kT phi minus phi n. So this is just a definition of phi n. It's like considering that phi n is defined as n over Ni with the log multiplied by kT over Q, and then we subtract phi. Okay, so this is a pure definition of phi n. Okay. Similarly, the definition of phi p is such that we can write the concentration P as Ni exponential of Q over kT phi p minus phi. Why do we adopt these definitions? Because if we are in the equilibrium condition, you remember N can be written as Ni times the exponential of Q over kT phi minus the Fermi potential, phi f, okay? So the two auxiliary functions, and the same for P, okay? The two auxiliary functions are new auxiliary unknowns that apply in the general case of the model, okay? And they have the property that in the equilibrium condition, they reduce to a constant, and this constant is the Fermi potential, okay? Why are these two new unknowns useful? Well, take the expression of n and take the gradient of it, okay? So the gradient of n, since n is an exponential, is equal to n itself times the gradient of the exponent. And the gradient of exponent is the gradient of phi minus phi n times Q over kT, and the Q over kT is shifted to the left, okay? So we have kT over Q times the gradient of n is equal to n times the gradient of phi minus phi n, okay? Similarly, kT over Q times the gradient of P is equal to P times the gradient of phi P minus phi, okay? Now we simply replace this expression of gradient of n into the drift diffusion equation, okay? Before that, what we can do is consider the drift diffusion equation for the electrons. You remember that the diffusion coefficient, dn, is equal to the mobility, mu n, times kT over Q. So we express dn in this form, okay? So we have kT over Q gradient of n, which is exactly the quantity that we have just calculated with the new definition, okay? So now, if you look at this expression for the current density of the electrons, the drift term is Q mu n times the electric field, but the electric field is minus gradient of the electric potential phi. So minus Q mu n and gradient of phi is just the drift term. Then we have the diffusion term, in which instead of writing the diffusion coefficient, we wrote mu n times kT over Q. And then kT over Q times the gradient of n is replaced with n gradient of phi minus phi n, okay? You see immediately that minus q mu n gradient of phi is cancelled. And we are left with minus q mu n gradient of phi n. So by using the new variable phi n, we have given the expression of the current density a monomial form. It is as if the gradient of phi n is a sort of a pseudo field embedding both the drift and diffusion components of the current. When we do the same analysis for the holes, we obtain a similar expression that is minus q mu p gradient of phi p gives the current density for the holes. Why are these expressions, or when are these expressions useful? They are useful for calculating the current in the devices in which one type of current is dominant. Okay, and this typically happens in the MOS device. Okay, in the MOS transistor, if the transistor is of the N-channel type, essentially the current is due only to the electrons. If it is of the p-type, the current is due essentially only to holes. So these are devices that are called unipolar because one class of charges is dominant for the transport. For the unipolar devices, it is preferable to calculate the current using the quasi-Fermi potentials. Okay? In devices like the bipolar devices, in which both electron and holes contribute to the current density and none of them is dominant, we shall use the customary expression of the drift diffusion type. Another issue related to the mathematical model of the semiconductor devices is, of course, the issue of the boundary conditions. Okay, you remember we have equations that contain the unknown functions and the derivatives with respect to space. Okay, and also they contain the derivatives with respect to time. Okay, but you know, for the derivatives with respect to time, we must prescribe the initial condition everywhere to the unknowns. Okay, so if we have a dynamic situation in which the time derivatives are present, we have to prescribe the initial condition. Okay. In space, instead, we have to prescribe the boundary conditions. Okay. To discuss this issue, we consider a very typical example, that of the MOS transistor. So let's consider the figure on the left. The figure on the left is a very schematic representation in 2 dimensions of the MOS transistor. You remember the lower thick line, this one, is the contact on the bulk, the bottom of the device. The 2 lateral thick lines are the contacts of the source and drain contacts, okay? And finally, the upper thick line is the gate contact. So the thick lines are contacts, okay? So typically these parts of the boundary are connected to a voltage generator so that we know the value of the voltage at the contacts, okay? Or if we are inside a circuit, we are anyhow able to calculate the value of the electric potential at the contact. Then there are other pieces of the boundary, okay? For instance, if you consider these two vertical lines, dashed vertical lines, okay? This is the portion of the device related to the gate oxide, okay? So this is an insulator region. Of course, there can be no current crossing the two lateral sides of the insulator, so they are insulating boundaries. So insulating boundaries are those boundaries that are not crossed by any current density, okay? This thin continuous line is not it's an internal boundary, okay, because it is the interface between the insulator that is on top and the semiconductor that is below, okay? And finally, we have the two lateral boundaries of the device. They are also to be considered insulating boundaries because if you remember, in the functioning of the MOS transistor, the current can flow only between source and drain. So if one of the two contacts here is the source and the other is the drain, the current enters the drain, goes across the channel and exits from the source, okay? It is impossible for the current to cross the lateral boundaries of the device. If that happens, that means that the design of the device is wrong, okay? Because we have a loss of current laterally, okay? So in general, we can always distinguish in a device two types of boundaries. Those that are insulating, that are not crossed by any current, and those that are contacts, okay, in which we know some information about the voltage, okay. By the way, we are considering a finite extension of the domain in which we have to solve the equations of the semiconductor model, okay? We never take domains that extend to infinity, like half a plane or so. We always consider, which is very reasonable, finite domains, okay? The structure indicated on the left in this page is very schematic, but not very realistic, okay? If you want to improve the description, first of all, the two source and drain contacts would be shorter, okay? So the figure on the right is more realistic because the source and drain contacts are shorter. They do not reach the point where the insulator begins, okay? So if they are shorter, then we have a decision to take, okay? How do we describe the insulating boundaries of the domain for the oxide, okay? Should we take it with a slope, like we did on the left, connecting the gate contact with the source contact, or should we take it with an angle, okay? Like we did on the right, okay? So we shall see, now we stop for 10 minutes, but we shall see in the next hour that the choice on the left is the correct one, and the other one is wrong. So we stop for 10 minutes now, and we shall resume at 4:10. Okay, so we'll start by considering the boundary conditions. And we now go to the next page. That shows a larger version of the picture that was on the right, okay? You remember when we consider the semiconductor device model, we can group the equations in order to have only 3 second-order equations, second order with respect to space. And the first of them has as unknown the electric potential. This is the Poisson equation. The second equation has as unknown the electron concentration, and the third one, the hole concentration. So let's start with the Poisson equation, that is a second order differential equation whose unknown is the electric potential. You remember from calculus that when you have a second order equation over a domain, the mathematical problem is well posed if the boundary conditions are such that the solution exists and is unique. A type of boundary conditions that are such that the problem is well posed with respect to an equation of the Poisson type is this. You must prescribe the value of the unknown along a portion of the boundary. And you must prescribe the normal derivative of the unknown along the remaining portion. Now, can we do this for our example? Well, consider now the contacts, okay? So the thick lines in the figure. At the contacts, you know the electric potential because you have voltage generators typically applied to the contacts, okay? So the value of the electric potential at the contact is prescribed. And this is a good boundary condition because the electric potential is the unknown of the equation and it is prescribed along the contacts, okay? We must remark that the contacts are not made of semiconductor, they are typically made of metal, okay? So there are interfaces at the contacts between metal and semiconductor, or between metal and insulator if you consider the gate contacts, okay? When you cross a boundary like this, an interface between two materials, you have a change in the electric potential. And this change is sometimes referred to as the difference in the work functions of the two materials, okay? So if you take the drain contact and you apply 5 volts to the drain contact, the semiconductor immediately underneath the drain contact has a potential that is not equal to 5 volts. It is equal to 5 volts less the difference in the work functions, okay? But this difference is given, is something that we know. So it is possible from the contact voltage to also deduce the voltage of the semiconductor that is attached to the contact, okay? So for the contacts, we do have a good boundary condition. And this is indicated as, you see the symbols, phi equal to phi c. That means the value of the electric potential is given by the electric potential at the contact, okay? Then we go to the case of the insulating boundaries, okay? Take the right part of the device where you have the dashed boundary that makes an angle, okay? Assume that the contact on the right is the drain contact and that you have applied, I don't know, 2 volts to the drain and 3 volts to the gate, okay? So the thin lines that you can see, those that make some curves, are the field lines that are in that region, okay? And the field lines start from the gate and close into the drain contact, okay? So you see that there is one field line that is the field lines with no slope, with no curvature, okay? That goes straight from the gate to the drain contact, okay? So along that field lines, the field is parallel to the line, to the thin line, okay? So along that line, the component of the field normal to that line is 0, because the electric field is fully aligned along the straight line, okay? So it is preferable, of course, to select the boundary along that line as it is done on the left, okay? So the dashed line with the slope that you can see on the left of the oxide is exactly parallel to the field line. So the field is aligned with the dashed line, which also means that the normal component of the field to that line is 0. But this also means that you do know the normal component, the normal derivative of the potential along that line, okay? So gradient of phi normal equal to 0 is also a good boundary condition, okay? In the mathematical nomenclature, prescribing the function at the boundaries is also called as Dirichlet boundary conditions. And prescribing the normal derivative at the boundary is also called Neumann boundary condition, okay? So since it is equal to 0, this is a homogeneous Neumann boundary condition. The same analysis possible along the dashed lines that describe the boundaries of the silicon region, okay? So as for the potential, we can state that the electric potential is given at the contacts, and this constitutes a Dirichlet boundary condition, and that we are able to select the insulating boundaries in such a way as to provide homogeneous Neumann conditions on those boundaries. So for the electric potential, the problem is well posed, can be constructed in such a way as to have it well posed, okay? Now we have to discuss the boundary conditions of the concentrations, okay? So if you look at the oxide, of course, the chiral concentrations are identically 0 inside the oxide, so there is nothing to solve, okay? The problem is already okay for the oxide regions, okay? So now we have to discuss what happens to the concentrations N and P at the contacts, source and drain, and bulk, and what happens to the normal derivatives of N and P at the two insulating boundaries that are on the sides of the silicon region, okay? For the contacts, the solution is relatively easy because the contacts are made of metals. Metals are extremely rich of free charge. They have plenty of electrons in them. So if you consider the semiconductor region that is immediately attached to the contact, if that semiconductor region in some sense tries to depart from the condition of charge neutrality, that is, if the charge density tries to become non-zero near the contact is immediately able to supply charge in order to restore charge neutrality. This is something that we can prove by calculation, but it would take too long, okay? So we have a condition in which near the contacts, that is source, drain, and bulk contacts in this example, we may impose a condition of equilibrium and charge neutrality to the semiconductor near the contacts, okay? And if you have equilibrium and charge neutrality, you remember you can immediately calculate the value of the concentration of electrons and holes near the contacts, okay? So for small n and small p, we also have Dirichlet conditions at the contacts, okay? So what is left is now the discussion about the insulating boundaries, okay? At the insulating boundaries, we can state that no current is crossing the insulating boundaries, okay? You remember the discussion 1 hour ago, okay? So we may say that the normal component of Jn and Jp, you can see it in the figure, is 0 at the insulating boundary. So we must now elaborate on this property that Jn normal and Jp normal are equal to 0 at the insulating boundaries of the semiconductor. So there is a short calculation that we can carry out. We already found that at the insulating boundaries, the normal component of the electric field is 0. Ni, in the first formula, is the unit vector normal to the insulating boundary, okay? So E dot Ni equal to 0 is equivalent to the normal derivative of the potential equal to 0, okay? But we also notice that at the insulating boundaries, the normal component of Jn and Jp are 0. So if you take, for instance, the drift diffusion equation for the electrons, the equation that gives you the expression of Jn, and project this equation over the normal unit vector to the boundary, and then force this to be 0, what you find is that you see here in the middle, this is the projection of Jn to the normal direction with respect to the insulating boundary, and this must be 0. So minus Q mu Nn d phi over dn plus q dn derivative of small n with respect to the normal is 0. But the first term is 0 by itself because of the Neumann condition on the potential. So the second summand here must also be 0, which means that the normal derivative of n is also 0 over the insulating boundaries. And by the same reasoning, you also find that also dp over dν is 0. In conclusion, all unknowns of the model have the same boundary conditions. Phi, n, and p are prescribed at the contacts. And phi, so they have the Dirichlet boundary conditions. And phi, n, and p have a normal derivative equal to 0 at the insulating boundaries. That is homogeneous Neumann conditions, okay? So we have three partial differential equations, one for phi, one for n, one for p, having the same type of boundary condition. So globally, the problem is well posed. We expect that if we solve it by numerical computation, we find a solution, and that solution is unique. In the next discussion, we have to face the problem of describing the coefficients of the model. So I go back for a second to the equations. You remember the coefficients of the models are the diffusion coefficient, the mobilities, and then the generation recombination terms, UN, UP, GN, GP, okay? We are now going to start with the description of the generation recombination terms. And you remember that we have distinguished between the thermal generation recombination events and the non-thermal generation recombination events, okay? So we shall now start with the general description of these events, okay? Now, this figure refers to the thermal generation and recombination events. We already had some short discussion of this issue at a much earlier stage when we were discussing the form of the bands, okay? But now we are going into it in some more detail, okay? You remember that it may happen that inside the gap of the semiconductor, this figure shows the conduction band on top, the valence band in the bottom, and in the middle we have the gap, okay? It may happen that in the forbidden gap of a semiconductor, there are energy states that derive from the existence of some defect of the semiconductor, like impurities or defects induced by deformation of the lattice, whatever, okay? It is impossible to have a semiconductor that is completely free of defects, okay? A type of defect or or energy states are those that are introduced by the dopants, as you remember. But they are very special because the states introduced by the donor dopants are very close to the edge of the conduction band. And the states that are introduced by the acceptor dopants are very close to the edge of the valence band. Okay, we are not considering these types of states due to the donor or acceptor dopants. We are considering other types of defects such that the energy states that are introduced by them are near the mid gap. They are in the vicinity of the intrinsic Fermi level that is indicated here with the dashed line. Okay. Now let's consider a transition of one electron from the conduction band into the valence band. So let's consider what we call a recombination event. You remember from some earlier discussion that a recombination event can be direct. That means that the electron may jump directly from the conduction into the valence band, releasing the total energy of the jump in one shot. This is called direct recombination. The opposite phenomenon is a phenomenon in which an electron initially in the valence band absorbs enough energy to jump into the conduction band, and this is called direct generation of the electron-hole pair. Okay. There is another phenomenon that is also possible, and this phenomenon is that if there is a trap, let's consider the phenomenon indicated with letter A. Okay. If there is an electron initially in the conduction band, this electron may release to the lattice, to the nuclei, enough energy to jump into the trap. The trap has an energy that is called ET, trap energy. Okay. This electron stays for a while in the trap, and then if you look at the event labeled C, this electron makes a second transition from the trap into the valence band. So globally, one event of type A followed by one event of type C globally is a recombination event. Okay, so it is made in 2 steps instead of 1. As you may remember, this is called trap-assisted recombination. The inverse phenomenon is also possible. You may have an electron that initially sits in a state of the valence band, absorbs energy from the vibrations of the lattice, and goes into the trap. So this is the event labeled D, okay? After a while, absorbs another block of energy and goes up into the conduction band. This is called event of type B. So D followed by B is a generation of an electron-hole pair, okay? All of these events are thermally activated. So the exchange of energy is within the vibrating nuclei of the lattice, okay? The issue is, which of these events are more probable, the trap-assisted ones or the direct ones? The answer is the trap-assisted events are much more likely to occur, to the extent that when we consider the thermal generations and recombination, we neglect the direct events because their probability is negligible, and we consider only these type of events, okay? For the description of the thermally assisted generation and recombination events, it is sufficient to consider only one type of traps, all of them with the same energy. This is a very simplified description, but we shall see at the end that it is sufficient, okay? But you remember that when we started discussing about energy states of the gap, in principle, we have two types of them. One type of them is the donor type, and the other type is the acceptor type, like in the dopants, okay? These are not due to dopants, but they behave like those of the dopants. They acquire or release electrons, okay? You remember that the donor traps have the property that they are neutral when they are filled with the electron and they are positive when they are empty. In contrast, the acceptor type traps are neutral when empty and negative when filled. So in principle, we should consider two more populations, so to speak, those of particles that are trapped in the acceptor type traps and those of particles that are trapped in the donor type traps, okay? So in principle, at least for the moment, instead of considering only two populations, electrons of the conduction band and holes of the valence band, for the moment, we will consider four populations. That is, electrons of the conduction band, holes of the valence band, and then we shall consider the population of the acceptor traps, and that is, it is useful to consider them as electrons trapped in the acceptor traps, okay? Because when populated, they are negative. And the fourth population is that of the donor traps that we consider as populated with holes, because when they are ionized, they are positive, okay? So just for a moment, we shall write not two continuity equations, but four continuity equations, and then we shall simplify them almost immediately, okay? So I go up one page, and you see here the set of four continuity equations for bands and traps, okay? The two equations for the bands are the usual ones, so nothing new. Those of the traps are written down simply by copying the corresponding equations for the bands and changing a little bit the symbols. So on the second line to the left, you see the continuity equation for the electrons of the acceptor type. So the population is called N sub A. The current density is called Jn sub A. The generation term is Gn sub A, and the recombination term is, the thermal recombination term is Un sub A, okay? Instead, still on the second line, but on the right, you see the continuity equation for the holes of the donor traps. So PD is the concentration of those holes, JPD the current, GPD the non-thermal generation, and UPD the thermal recombination, okay? All these calculations are used to determine the expression of the thermal recombination terms, okay? So we simplify the model by considering that there are no non-thermal events, okay? So we set all the G's to 0, okay? After that, we add the equations one to the other by taking the equations corresponding to the holes with the positive sign and the equations corresponding to the electrons with the negative sign, because electrons are negative, okay? So for instance, we group first all the terms that are under the time derivative. So you see we have dp dt, it goes here, dp dt, plus dpd dt, it goes here, less dn dt here, less dna dt here. And then we add the dopant. Why? Because the dopant can be added safely, because the dopant profile does not depend on time. So actually, it is added under the time derivative, so it is 0. The time derivative is 0, okay? And finally, we multiply by the electron charge, okay? Then we have divergence of Jp plus divergence of Jpd. Then the others change sign. We have plus divergence of Jn and plus divergence of Jna, and we brought the charge to the left, okay? And then we have the thermal recombination terms. So this is equal to Q UN plus UNA minus Q UP plus UPD. If any of you has a paper copy of the notes, here there is a misprint. In this line, in the paper version, symbol Q here and here is missing. So if any of you has the note in paper form, please add symbol Q here and there and the parentheses, okay? Now you see immediately that we have a global continuity equation in which we have the time derivative of all contributions to charge density, because there is the population of the holes of the band, the population of the electrons of the band, the population of the trapped particles, PD and Na, and finally the dopant. So the time derivative is the time derivative of the global charge density of the semiconductor with all contributions present. The divergence operator also embeds all possible currents. Okay, so this equation is the continuity equation from the Maxwell equation directly, so it must be 0. That means that the right-hand side must also be 0. So Q parenthesis UN plus UNA minus Q parenthesis UP plus UPD is 0, which means that UN plus UNA is equal to UP plus UPD. This is a fundamental result, which can also be found by reasoning, okay, instead of doing a calculation. All these transitions are transition of electrons on the left and transitions of holes on the right, okay? But a transition of an electrons is also a transition of holes in the opposite way, so they must be equal, okay? So we have a general relation of this type with no simplification. This is fully general. Now we introduce a simplification, okay, by observing the nature of JPD and JNA. What is JPD and what is JNA? Let's go to the figure. Assume that these traps are of the acceptor type, okay? So we are considering JNA. JNA is a current along the traps because of the meaning of the continuity equation. So it indicates a current density that goes from one trap to another, to another, to another. So it describes a current that flows across the traps, okay? The question is it possible or not? In crystalline silicon, it is impossible practically. Why? Because the only mechanism by which one electron can move from one trap to another is the quantum effect that is called the tunnel effect, okay? And the tunnel effect becomes significant if the two traps are very close to each other, if the distance between the two traps involved in the tunnel effect is small, okay? In crystalline silicon, traps are not so many. So the relative distances among traps are large, and this prevents the tunnel effect from occurring, okay? In polycrystalline silicon, instead, it happens because there are so many traps in the polycrystalline silicon that the tunnel effect is non-negligible, okay? So at this point, we neglect the currents, okay? So now look back at the two equations, the two continuity equations in the second line, okay? We neglected GNA and GPD. Now we are neglecting the currents because there is no tunnel of particles from one trap to another. So these two equations reduce to the equations that are written here. The time derivative of NA is equal to minus UNA, and the time derivative of PD is minus UPD. So the two continuity equations have become local. There are no space derivatives anymore. Now we may distinguish between two situations. If we are in a situation of non-equilibrium, but steady state, that means that nothing depends on time, the two time derivatives here and there are zero. So UNA and UPD become zero, although we are in a non-equilibrium condition. And from the general relation above, we deduce that UN and UP are equal to each other. You may remember when we introduced the symbol W for the global generation recombination term, we said we are using two symbols, but at the very end, there will be only one function because they are equal to each other. Now we are approaching that point, okay? In steady state, UN and UP are rigorously equal to each other, so we can use one single symbol U, okay? In a dynamic condition, in principle, they are different, okay? But yet, the populations of NA and PD are so small that their contribution to the phenomena is negligible. So also, in the dynamic condition, we neglect approximately UNA and UPD. So in general, we shall take from now on that the two thermal recombination terms UN and UP are equal to each other, okay? And so we shall use one single symbol from some point on for them, okay? Now the issue is to calculate the expression of U, okay? So as you have seen, we introduced 4 equations, but then we are back to 2 continuity equations, okay? The calculation that provides the net thermal recombination rate U is due to this gentleman, Shockley-Ritz-Hall. So it is called the Shockley-Ritz-Hall theory, okay? What we do is treating separately the possible events that concur to determining UN and UP, okay? So you see in the figure, we already commented a little bit. We assume that there is only one type of traps, and that all traps have the same energy that we call ET. These traps also have a concentration in space, okay? And this concentration in space, the equation below, is called capital NT. So NT is the concentration of the traps, okay? And then we distinguish first events of type A. Events of type A are the transition of an electron from a state in the conduction band into the trap. You remember that electrons don't like to stay together. So for this electron to make this transition, it must happen that initially the trap is empty. If the trap is already filled, it is impossible for another electron to make the transition. Then we have transition of type B. One electron initially belonging to the trap makes a transition into the conduction band. So obviously, the total events of type A less the total events of type B per unit volume and time gives you the net recombination rate of the conduction band, because we have everything that goes out less everything that comes in. Then we have events of type C, in which one electron initially belonging to a trap makes a transition into an empty state of the valence band. This is also described as a transition in the opposite direction of a hole. So we have like a hole initially in the valence band makes a transition into the state. And finally, we have one electron of the valence band going into an empty trap that we describe as the opposite transition of a hole from the empty trap into the band. So obviously, events of C-type less events of D-type per unit volume and time provide the net recombination rate of the valence band, okay? Now let's give some names to these rates. RA is the number of events of type A per unit volume and time. RB is the number of events of type B per unit volume and time. So UN is obviously the difference between RA and RB. Next, RC is the total number of events of type C per unit volume and time. RD is the total number of events per unit volume and time of type D. So obviously, UP, for the moment we keep the two different symbols, okay? UP is the difference RC minus RD, okay? Remember, we are in a non-equilibrium condition. In equilibrium, UN is identically zero, UP is identically zero because the continuity equations are identically zero, okay? So we are in a non-equilibrium condition, okay? So the probability of occupation of the electron state cannot be described using the Fermi statistics. The probability of occupation is unknown, okay? Specifically, we shall call with the symbol PT the occupation probability of the traps of energy ET. So this PT is something that is unknown in a non-equilibrium condition. It becomes the Fermi statistics if we are in equilibrium, but in general it is unknown, okay? What we shall do next, we shall give an expression to RA, RB, RC, and RD. So eventually we shall have an expression for UN and UP, okay? And then we shall remember that UN and UP are equal to each other. So we shall put the two expressions together. We shall put them equal to each other, okay? And after some other calculation, we shall be able to find the common value of the two. So now we stop for a few minutes. We shall start again at 5:40. If there are questions, please ask them now. Otherwise, we shall meet each other again in about 10 minutes. Okay, so what we are left with now is determining separately the expressions of rates RA, RB, RC, RD. Okay. They can be found by a longer calculation, but we find them heuristically, starting, for instance, from RA. Okay. RA, I remind you, is the number of transitions of type A per unit volume and time. So it is the number of transition of electrons that initially are in the conduction band. So one may argue that the number of transitions would be proportional to the number of electrons that are present in the conduction band. The more electrons are present, the more transition we expect to have, okay? So we start by setting RA proportional to the concentration of the electrons of the conduction band, okay? But also, it is intuitive that the number of transitions will be larger if the number of traps is larger, okay? If we had no traps, we would not have any transitions, okay? So the number of transitions of type A must also be proportional to the number of traps, but not just the number of traps, the number of traps that are empty. Because if a trap is already filled, it cannot be reached by another electron. So we set RA also proportional to the concentration of the empty traps, and the concentration of the empty traps is equal to the concentration of traps, NT, times the probability of being empty. So if we indicate with symbol PT the probability of occupation of the traps, then 1 minus PT is the probability that a trap is empty, okay? Multiplied by the concentration NT provides the concentration of the empty traps. And finally, we put in front of it a coefficient alpha sub n. This coefficient is called the transition coefficient. Its units are those of a volume divided by a time, and this transition coefficient alpha sub n describes the physics of the interaction between the electron and the trap, okay? So this is it for RA. Then we have to describe RB. RB is the opposite mechanism. It's the transition, is the number of transitions from the trap into the conduction band per unit time and volume, okay? So of course, RB must be proportional to the number of traps that are filled. And this number, sorry, this concentration, the concentration of traps that are filled, this concentration is equal to the concentration of the traps NT times the probability of being filled, okay? Then we should also consider the probability that the arrival state that belongs to the conduction band is empty, okay? But this probability is practically equal to 1 because you remember the majority of the states of the conduction band are empty, okay? So we don't put it in, okay? We imply that this probability has been accounted for. It is practically equal to 1. And then we have a coefficient that describes the emission from the trap into the conduction band. This coefficient is called the emission coefficient, E sub n, and its units are those of the inverse of a time. Next, we must describe RC and RD, but the description is similar. So RC must be proportional to the concentration of holes of the valence band, to the concentration of filled traps, because the transition of a hole into the trap happens if the trap is filled. So we have P times NT PT times the transition coefficient for the holes, alpha P. And the last phenomenon, type D, is the emission of a trap, of a hole from the trap into the valence band. So it must be proportional to the concentration of empty traps, NT1 minus PT, times the probability that the final state is filled with an electrons, but this is practically equal to 1 because almost every state of the valence band is filled. And finally, we have the emission coefficient of the hole, E sub P, okay? So we have these two separate expressions, okay? But we know that they are equal to each other, okay? It's intuitive that if the parameters are known, if alpha n, alpha p, en, ep, and the trap concentration is given, when we put un equal to up, we obtain an expression involving small n, small p, and the probability pt of occupation of the traps. So it's one expression. We can express this probability as a function of np and parameters, so we are not introducing any additional unknown to the semiconductor model, okay? Prior to that, we can try to understand whether the parameters are fully independent or not, okay? Actually, we can show that there exists a relation between the emission coefficient En and the corresponding transition coefficient, alpha n, and a similar relation exists between EP and alpha P. For this, we impose the equilibrium condition. So we calculate UN and UP separately in the equilibrium condition, but you remember at equilibrium UN is 0 and UP is also 0. Okay, so at equilibrium RA is equal to RB. And similarly, RC is equal to RD. On the other hand, at equilibrium, N and P are known because they are the equilibrium concentrations of the electrons and holes. And PT becomes the Fermi statistics, okay? So this allows us to find the relation between the emission coefficients and the transition coefficients. So we do this first. It's quite easy. Take this difference and put it equal to 0 at equilibrium. NT cancels, okay? And then divide both terms by PT. Okay, so you leave En alone. When you do this, you find En equal to alpha n of equilibrium, 1 over P minus 1, and Pt is also the equilibrium statistics, okay? So it is a modified Fermi statistics. You remember that when we have discrete states, discrete in space, okay, we must consider the degeneracy coefficient, so dt. So at equilibrium, Pt is 1 over dt exponential of what? Of the trap energy, of course, because Pt is calculated at the energy trap, minus the Fermi level over Kt plus 1, okay? In this relation here, we have 1 over Pt minus 1. So 1 over Pt is the denominator, and minus 1 is the denominator without this plus 1, okay? So 1 over Pt minus 1 is simply 1 over dt times this exponential, okay? And we can replace it in here. At this point, you observe that n of equilibrium is something that we know. The degeneracy coefficient is a pure number that we know, like 2, okay? And this exponential is also a pure number that we know because we assume that we know the position of the traps, okay? So n equilibrium divided by a number times another number is still a concentration. We call it NB. So NB is n equilibrium over dt times the exponential. It is something that we know. So you see, E sub n is equal to alpha n times NB. So E sub n and alpha sub n are not independent parameters, okay? If you know one of them, you know the other. If you do the same analysis with the holes, you find EP equal to alpha P times PB. Notice that PB is P of equilibrium times the degeneration coefficient times the same exponential as before with the opposite sign in the exponent, okay? Now, we shall not use E sub n anymore. We shall use alpha n NB for it. And we shall not use anymore E sub p. We shall use alpha p PB in place of it, okay? Now we remember, we go in a non-equilibrium condition again, and we remember that Un is equal to Up. So we put these two quantities equal to each other, okay? There is a proviso, okay, that the relations between En and alpha n have been found in the equilibrium condition. Are they still valid in a non-equilibrium condition? Approximately they are, okay? It can be shown that these two relations, En equal to alpha n times Nb and Ep equal to alpha p times Pb still hold in a non-equilibrium condition, okay? So now we take the expression of Un, this one. We put it equal to the expression of Up. Again, the concentration of the traps cancels everywhere. And we have this relation, this one. alpha nn times 1 minus pt E minus alpha nb pt equals this other expression, okay? So you see immediately that it is linear with respect to pt. So we immediately find the expression of pt, this one, okay? Note that the expression of pt, the denominator d is this, okay? So the expression of pt is the expression of the probability of occupation of a trap expressed as a function of the concentrations small n here and there and small p of electrons and holes and parameters. Okay, so we can express pt without introducing additional unknowns into the model. And remember, we are using both pt and 1 minus pt. So this is the expression of 1 minus pt, okay? Then we take pt and 1 minus pt and replace them back into either the expression of un or the expression of up. We obtain, of course, the same expression at the end because un and up are equal, okay? So eventually we obtain the common expression of un and up. We replace pt and 1 minus pt in the common value. We obtain this, okay? It looks complicated, but it is not, okay? Because first of all, there are terms in the numerator that cancel out. You see immediately that we have alpha n, alpha n, and b, and again we have alpha n and b, alpha n. They cancel, okay? So in the numerator we have np, this one, multiplied by alpha n, alpha p. And then we have here nb/pb, again multiplied by alpha n, alpha p. We divide the numerator and the denominator by alpha n, alpha p, and t, and we obtain this simplified expression, okay? You see that this simplified expression is the product NB/PB. What is it? Well, NB/PB is the product of n equilibrium over dt times this exponential times p equilibrium dt times the opposite exponential. So the exponential cancel, dt and dt cancel, and we are left with n equilibrium times p equilibrium. So this product here is actually the equilibrium product of the electrons and holes. And to come to this point, we did not use any simplifying hypothesis. We never assumed that the semiconductor is non-degenerate. It may be still degenerate, okay? This expression is correct anyhow, okay? Of course, n equilibrium and p equilibrium, if we are in the degenerate case, should be expressed as Fermi integrals, okay? Now we make the simplifying hypothesis that the semiconductor is non-degenerate, So we can say that NPPB is the usual Ni squared expression of the equilibrium product of the non-degenerate case. Okay? This also implies that NB can be simplified, okay, because it's a calculation for which we would need the blackboard, but remember, in the non-degenerate case, N equilibrium is Ni, sorry, capital NC, the effective density of states of the conduction band, times the exponential of EF minus EC. So EF cancels here, and you are left with, in the non-degenerate case, NB is NC times the exponential divided by dt. Similarly, PB is equal to NV times dt times the exponential minus ET minus EV over KT. Okay, so at this point, if you look at the expression of U, remember, in the non-degenerate case, this product is equal to Ni squared. So it does not contain the energy of the trap anymore. So globally, the numerator of this expression does not contain the energy of the trap. Instead, the denominator does, because NB here, you can see it below, is proportional to the exponent of ET over KT. And PB is proportional to the exponent of minus ET over KT. Okay? So the trap level at the very end in the non-degenerate case appears only in the denominator of U. Okay? Now we have to go back, because you remember when we started the analysis, we said we always have traps in the gap. And since we always have traps in the gap, then the direct transitions will be negligible, because the trap-assisted transitions are the only ones that are important. Okay? But the point is, we made the calculation assuming that there is only one level of traps. But this is clearly not true. We may have different families of traps with different energies. Okay, so what should we do now? In principle, we should repeat the calculation for each trap energy that is present in the semiconductor and sum up the results. Okay? This would be very inconvenient, okay? And we ask ourselves, should we really do this? Fortunately, we are not going to do it, because consider the expression of U, okay? We ask ourselves, how does U depend on the trap energy? Well, it is visible here. The trap energy is embedded in NB and PB only. NB depends exponentially on the trap energy with the plus sign. So NB increases very much when the difference ET minus EC becomes more and more positive, okay? PB increases very much when ET minus EV becomes more and more negative because of the minus sign in the exponent, okay? So the denominator of this expression in all cases depends exponentially on the trap level. So we may pursue this analysis. We say, let's take the value of the trap energy that provides the minimum of the denominator. For that energy, since the denominator is a minimum, U will be a maximum, okay? And this is, of course, the energy of the traps that is the most important because gives the maximum of U. When we go away from that value of ET, the denominator increases exponentially, so it will kill U, the recombination function, okay? So actually, the only trap level that is important is the trap level for which the denominator has a minimum. It is very easy to calculate the minimum of the denominator because they are just exponentials, okay? So we take the derivative of the denominator with respect to ET, and then we put it equal to 0. And what we find is that the value of ET that provides the minimum of the denominator, that is the most efficient trap energy for the transitions, is this one. Okay. Now, if we examine this expression, we see that 1/2 EC plus EV is just the mid gap. The other expression is small because KT, as usual, is small with respect to the mid gap, okay? Also, the degeneracy coefficient is order unity. NV and C, you remember, are similar. Alpha P, alpha N, we did not calculate them, they are also similar. So the parenthesis here, the argument of the logarithm is near 1, so the logarithm also is very small, okay? So apart from a small correction, the most efficient value of the trap energy for the trap-assisted transitions is the mid gap, okay? So we simply neglect all the other traps with different energy. We keep only the traps at the mid gap as the most efficient ones. So we keep this expression of U. Besides, if we consider that ET is near the mid gap, we find immediately that NB and PB become very similar to the intrinsic concentration, not exactly equal because of the degeneracy coefficient, but the order of magnitude of NB and PB for the energies of the traps that are near mid-gap is Ni. This is also important, okay? Given these simplifications, we may still manipulate a bit this expression. We know that NBPB is Ni squared, okay? We manipulate a little bit the denominator because we have NT alpha P and T alpha N. You remember, NT is a concentration. Alpha P, alpha N are dimensionally volumes over a time. So these products are the inverse of a time, and this is also the inverse of a time. So we introduce new symbols. The lifetimes, tau P0 is defined as 1 over NT alpha P, and tau N0 is 1 over NT alpha N. Expression for U is this. Observe that tau P0 multiplies N plus NB, and tau N0 multiplies P plus PB. Okay. This function, since the derivation is due to Shockley-Reed-Hall, is also called the Shockley-Reed-Hall recombination, and it is indicated with the symbol USRH, okay? How does this expression behave? Consider the equilibrium case, okay? In equilibrium, obviously, NP becomes equal to the equilibrium product, okay? Ni squared is the equilibrium product. So in equilibrium, the numerator is 0 and U is 0 as should be, because in the equilibrium situation, the microscopic balance condition tells you that all the generation and combination terms are individually equal to 0, okay? If you are in a non-equilibrium condition, you may have that in some regions of the semiconductor, the product NP is larger than the equilibrium product. So U is positive. You remember, U has the meaning of recombination less generation. So if U is positive, that means that recombination prevails over generation. So when there is an excess of charges such that the product NP is larger than Ni squared, the semiconductor in that region recombines more than it generates. In regions where NP is smaller than Ni squared, the opposite happens. So generations prevail if there is a lack of carriers. Okay. At this point, you remember U is one of the terms that appears in the mathematical model of the semiconductor devices. So we shall simply use this formula for U. It depends only on N and P, so it does not introduce any additional unknown with respect to those that appear in the model. On the other hand, it is non-linear, of course, with respect to N and P, okay? We must take it, okay? When we solve numerically the semiconductor equation, we just provide this expression to the computer and that's it, okay? In analytical calculations, sometimes it is possible to simplify the net recombination term, okay? And actually, there exist two limiting cases that occur very often in the analysis of semiconductor devices, okay? One limiting case is called full depletion. Full depletion is the condition of a region that may occur in some working condition of the semiconductor, such that in that region the electron and hole concentrations are negligibly small with respect to the intrinsic concentration. And you remember the intrinsic concentration NB and PB are of the same order, okay? So full depletion occurs when N and P are much smaller than Ni, NB, and PB, okay? So you can see immediately that the expression of U simplifies strongly because the product NP is negligible with respect to Ni squared. Then we neglect N with respect to NB. We neglect P with respect to PB, okay? So we obtain a simplified expression that is U. It's a constant, okay? There are no variables anymore in it, okay? So in full depletion, U is equal to minus Ni squared divided by tau P0 NB plus tau N0 PB, okay? The minus indicates that generations prevail over recombinations because we have a lack of carriers, okay? We may further simplify the expression because NB is almost equal to Ni, PB is almost equal to Ni, so we cancel approximately Ni in the numerator and NB, PB in the denominator. So we have this simplified version, okay? And the sum tau P0 plus tau N0 is given the name tau G. It is also called the generation time, okay? Because generations prevail over recombination. So in full depletion, we have a very, very simple expression of U. It is just a negative constant, okay? Another limiting case exists of the net thermal recombination rate. And this other limiting case is called weak injection. To define weak injection, we need a region where the semiconductor is doped. So we must be able to distinguish between the majority carriers and the minority carriers, okay? The weak injection condition is this: the absolute difference between the actual concentration of the electrons and the equilibrium concentration of the electrons, and at the same time, the absolute difference between the concentration of holes and the equilibrium concentration of holes. Both these quantities must be much smaller than the equilibrium concentration of the majority carriers, that is indicated here with the general term, general symbol C equilibrium, because we did not specify yet whether we are in a P region or in an N region, okay? So the weak injection condition must be calculated twice because it changes depending on being in an N-doped or P-doped region, okay? So we had to perform the calculation twice. Now take the N-type semiconductor. So C equilibrium becomes N equilibrium, okay? The numerator of U simplifies, okay? We can do the calculation easily if you think of considering the electron concentration N as N less N equilibrium plus N equilibrium. And then you replace P with P less P equilibrium plus P equilibrium, okay? And then you neglect terms with the product P minus P equilibrium times N minus N equilibrium, because they are small individually, so they are even smaller in the product, okay? So the numerator becomes this. In the denominator, since the electrons are the majority carriers, N is much larger than NB, because NB is of the same order as Ni, okay? But also N is much, much larger than P, because P is the minority carrier. And N is also much larger than PB, because PB is similar to Ni. And the lifetimes are similar, okay? So of the four terms in the denominator, only one survives, the first one, and we approximate N with an equilibrium because of this inequality here, okay? At this point, the net recombination term splits into two parts. One part is the part corresponding to P minus P equilibrium, this one, okay? You see that N equilibrium cancels. So this is the first part. And the second fraction is this. Then the second fraction is much smaller than the first fraction. Why? Consider a dopant concentration of the N zone equal to 10 to the 16th, okay? So you remember, N equilibrium is practically equal to 10 to the 16th. PD equilibrium is equal to Ni squared divided by N equilibrium. So it is 10 to the 20th divided by 10 to the 16th. So the concentration of the holes is 10 of equilibrium is 10 to the 4th. So here you have N equilibrium equal to 10 to the 16th divided by 10 to the 4th. So we have 10 to the 12th, okay? So the second fraction has a denominator that is the same tau P0 as the first one, multiplied by 10 to the 12th. That is enormous, okay? So you can safely neglect the second fraction, okay? And then you also simplify the symbol. You call tau P0, you drop the 0, you call it tau P, okay? Conclusion, in the weak injection condition, if we are in a zone that is N-type, then U depends only on the minority carriers. That depends only on P, okay? It is equal to P minus P equilibrium over tau P. Conversely, if you are in a P-type region, by the same reason, you find that by the weak injection condition, if the weak injection condition applies, then the net recombination rate is practically determined only by the minority carriers, that in this case are the electrons. This result is extremely important for two reasons. One reason is that U becomes linear, okay? Either with respect to N or to P, okay? So it is a linearization of U. The second very important conclusion is that U depends only on one type of carriers, okay? Because of this, it becomes possible, we shall see many examples of it, okay? Each time we can apply the weak injection condition, we can decouple the equation of the model from one another, because we have U depending on only one type of carriers. Having the equations decoupled is extremely useful. It's an extremely powerful method for solving them, because we solve them one at a time, okay? Instead of having a system of equations, we have individual equations that, of course, are much easier to solve. So the subdivision of the domain of a semiconductor into regions, in which some of them are in the full depletion condition and the others are in the weak injection, is extremely useful for solving analytically the semiconductor model. Of course, if we are doing a numerical solution, we don't care. We use the full form of the net recombination term. But if we have to proceed analytically, this approach is extremely powerful, okay? So this concludes the analysis of the thermal recombination rates that are the most important ones, okay? Next week, we shall see something about the other mechanisms of generation recombination in order to complete the model, the analysis of the model for the semiconductor devices. After that, we shall start considering individually the most important devices and sensors that constitute the second part of this course. So for the moment, we stop. If there are questions, you can operate the mic and ask them. Otherwise, or use the chat if you wish. Otherwise, we shall meet each other again on Tuesday. Thank you.